Good morning, ladies and gentlemen. We're here today to look at graphing, right? You may ask yourself, why is it important for me to know graphing? Well, first and foremost, at least 85% of the labs that you'll be doing, right, will require for you to be able to plot and analyze a straight line graph effectively. So then, obviously, you must be able to plot and analyze a straight line graph. And also, as I said, this is a very dynamic environment. I can always turn up to the class and give you a pop quiz. And I may very well give you something that requires for you to plot and analyze a graph. So you must be able to, right? And secondly, in our field of study, physics, which is physics, right, we use graph to make prediction. We also use graph to find unknown values, unknown constants, right? So then it is very, and I must emphasize, very important for us to be able to plot and analyze graph effectively. All right, let's cut the chase. Now, we all know that the general equation of a straight line graph is y is equal to mx plus c, right? And each of these components must either be what? It can either be a constant or a variable. And let us look at that in a little bit of detail. Now, let's say we capture some data for y and x. So then y slash some form of unit and x, whatever unit x bear, right? And let's say we have 3, 5, 7, 9. And we have 1, 2, 3, 4. So then, basically, what is happening here, when y is equal to 3, x is equal to 1. When y is equal to 5, x is equal to 2. When y is equal to 7, x is equal to 3. When y is equal to 9, x is equal to 4. Now, let us just take up this one here and put it in this equation here. So then we say, for y is equal to 3. So 3 is equal to m, and x is equal to 1 times 1 plus c. Right? And right here, this one here, 5 is equal to m times 2 plus c. So then, obviously, we have two unknown right here. This and that, this and that, right? So we must be able to find these unknown, right? So then what we recognize here is that one moment y is equal to 3, the next moment it is equal to 5, the next moment it is equal to 7. So then obviously y is a variable. It is a variable. One moment it is storing 3, the next moment it is storing 5, the next moment it is storing 7. So then it is a variable. And the same thing for x. One moment it is storing 1, the next moment it is storing 2, and then the other moment it is storing 3. So it is also a variable. Now, let us look at this here in detail and see if we can come up with this M here and that C, right? So then we say that our general equation of straight line is y is equal to mx plus c. Now, let us plot this on our graph paper. So then, this is my table, and this is my graph paper here. Right. First and foremost, you must come up with a scale in the system that will allow you to plot a curve that will cover at least 75% of the graph paper, right? The curve must cover at least 75% of the paper, right? So then, this is my scaling system, and my y, which would be my dependent variable, because this here depends on this and what these work out to be, to give you that. So then this is my dependent variable. You must always put your dependent variable on your vertical. Some persons refer to it as the y-axis, but I love to say vertical, right? So we say y/unit, and then this axis here, which is my horizontal, we say that x/unit. So then therefore I label my axis. That is the first thing I need to do. The next thing is that I need to give the graph a title. So then this is graph of y versus x. And then I must come up with my scaling system. So then, first and foremost, we know that y is equal to 3 right here. Then 5, 7, and 9. So then we're working with 4 different values for y, right? It wouldn't be wise to say, okay, so then this is 1 right here, this is 2, that is 3, that is 4, that is 5, that is 6, and that is 7. No, that would be a poor scaling system. And then we say this is 1, 2, 3, 4. When we start plotting this, so we're saying 1 with 3, 2 with 5 right here, 3 with 7, 3 with 7, and 4 with 9. So 8, 9. 4 with 9. This graph here would cover just about 20% of the paper. But this is a poor representation of our data. We don't want that, right? So you come up with a good scale that will cover at least 75% of the paper. So then you'd say, all right, this will be about 1 because we're having 4, 2, 3, 4. So then this is 1, 2, 3, 4 on our x-axis. And on our y-axis, we can say, all right, so this will be, let's say this is 1, 2, 3, 4, 5, 6, 7, 8, 9. You see, cover the entire range as best as possible. So now this is my 1, 2, 3, 4, 5, 6, 7, 8, 9. Now let us plot. So then we have 1, with 3. You can either put a dot with a very dark pencil, or you may put a little X to mark the spot. 2 with 5. Right? And when you're doing your graph, you wouldn't have to put this dot, 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 because the thing would be properly ruled. In my case here, it is not ruled, so I'm just giving you the best approximation. Alright? 3 with 7. Right? And 4 with 9. And then we'd have a ruler. So you take your straight edge and you draw the best straight line. And our best straight line should be in such a way where the points are what? Evenly distribute around the line itself. Right? So then, let's say we have something that looks like this. And then we draw something like that. Sorry. Right. This would be a poor representation, right? Because these points are not evenly distributed around the line itself. So then, if I have something that looks like this, that would be a better representation, because what we recognize that the points are evenly distributed, even though the line doesn't consist of any of the points. You notice? Right. So it doesn't mean that the point have to fall on the line in order for the line to be the best representation, right? So then, but in my case, they're fairly lined up evenly. Let me look. Right? So then, and that would be my best straight line. Alright? Now, so we know how y, and these will be my y values. We know the x, but what about m? For the straight line graph, m is known as the gradient. Some persons would say the slope. Some person would say rise over run, right? So then m, which is equal to the slope, which is equal to y1 minus y2 over x1 minus x2, right? Okay. So then, in order to get my y1 and my y2 and x1 and x2, you just pick two extreme points on your graph. Let us call this one here P1, and then you capture the coordinate. So then P1 would consist of y1 and also x1. P2 would consist of y2 and x2. You can put a little comma right here. Right? So let us put some values to it. So then y1, what is my y1? In this case, my y1 would be 9. So you say 9 minus y2, my y2 here would be 3 over x1, my x1 here would be 4. x2, my x2 here would be 1. And that is 6 over 3, and that is equal to 2. And I explained to you earlier that y would be a variable because y will take on various values, right? And x is also a variable. But let us see if m, or the slope, is a variable for the straight line graph, right? So now let us just choose two different points, right here and right there. So then this now would be my P1, and the coordinate would be 7 and 3, and call this one here P2, and the coordinate here would be 5 and 2. So then the slope is equal to my y1 here would be 7 minus 5 over 3 minus 2, and that is equal to equal to 2 divided by 1, which is also equal to 2. And what we recognize here is that in the first scenario we get 2, and also the second scenario we also get 2. So then what we notice is that what? M will never change. So then we say that it is a constant. So then this is a constant for a straight line graph. For a straight line graph, M is a constant. It will never change, right? And C is our intercept. This is where the curve cuts the vertical axis. So where this cuts right here, and then you read off this value here. If this was properly ruled, then you could just read off this y value here. Right? And that would give you your C. So then this is my general representation of a straight line graph. Alright, folks. Now, I'm going to erase this. Alright, now in our field of study, we must be able to link this equation here with various equations that I will give to you, right, in our lab setting. For example, let's say I give you a clamp stand, not a very good artist here. I also give you a pendulum, a stop clock, and I also give you a ruler. And I said to you that I want you to use these equipment and this equation here. T is equal to 2 pi square root L over G to find a value for gravity in your particular location, right? Whereby T is the time for one swing or one oscillation of the pendulum, to and fro. So then let's say we pull the pendulum to this. Give me a second. Let's say I pull this pendulum here to the side like this, and I release it and it comes back. The time it takes to do that to and fro, right? That is equal to T. And that is equal to what? 2 pi square root L, which would be the length of the pendulum from the center to the tip up here, right? That would be L over G, where G is gravity. And let's say our aim is to find G. Now, if you should take the timer and also just take one swing like this, so then you're going to start the timer concurrently, so you do and capture the time like that, right? To capture T, and you measure L right here, and 2 pi, and you have your 2 pi, and then you're going to transpose and make G the subject of the formula, right? Yeah, that can work, but that would be a very crude way of doing it, right? Very, very crude way, because when you do this, we have so many random errors that could occur, right? And we must be able we must be able to eliminate our random errors, right? So then if I take my timer and I take one swing like that and try to capture the time for the to and fro to get T right here, that would be a very crude way of doing it. So we must be able to what? Try and analyze, try and eliminate those random errors, right? But what if instead of doing one swing, we take, let's say, 20 swings, right? So then we pull the pendulum to the side, we release it, allow it to settle down, and then we start the clock timer. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and then we stop the timer. And you capture a particular time. So then the time, let's say for argument's sake, the time that you capture is 15 seconds. So then 15 seconds for 20 swing, right? And that would be small t, right? What is the time for one swing, which would equal to big T? That is the question. And the answer is, you simply divide the 15 seconds, because this represents 20 swings, so then one swing would equal to the 15 divided by 20, right? So then if we have T, it is equal to 15 divided by 20. 15 divided by 20. And that would be 15. That would be point. You put a 0 right there. And 20 into 150 is equal to 7. 7 times 20 is equal to 140. And that is equal to 10. And then we drop our next 0 right there. And we say that 20 into that goes 5 times. Right? So then big T is equal to 0.75 seconds. And that is the time for one complete oscillation. Right? So then basically what we do is to take an average. And when we take an average, basically we eliminate our random errors as best as possible. Right? So then obviously we'd have to come up with a wonderful table to suit this equation here. So then we would come up with what are the variables here? What could be our variables here? What can I change? What can I alter to change this value here? Can we change 2? No, you can't. So then 2 is a constant. Can you change pi? No, you can't. Pi is a constant. Can you change g in your particular location? Absolutely not. Right? G is also a constant. But can you change the length of the pendulum? Yes, you can. Right? So then L can be our variable. And if we change L, what happened to T? Yes, it would what? Automatically change T. Because mathematically, if you change this value here, all of this would change. And then, in turn, that would also change. Right? So then, we would have our L. It is a variable. And the unit for L is meter. And also we have small t, which will be the time for our 20 oscillation. Sorry. And then we could have T2 / second. And then we have what? T average, which would be this plus that divided by 2. We get T average. And then now we get big T. And big T we get big T, right? So then it is T average divided by 20, and that will give you big T. So then obviously we need to capture this equation here in the table, right? In order for us to plot a suitable graph. So then, okay, so then you could plot T, because we know now how to get T. You simply get T1 plus T2 divided by 2. You get T average. And T average divided by 20 going to give you big T. Wonderful. The next variable here is L, but it's not just L. It is L to the half. So then if we rearrange this equation here to the half, it's the same thing as saying square root. Now, so then we don't have L in the equation. We have L to the half. So then obviously we need a new row, and we're going to call that one there L to the half. But really and truly, I don't like to work with square roots, because guess what? You're going to get some small values. And then the maths can be very involved, right? And as mathematicians, we like to make our lives easy, right? So then, obviously, right, it would be good for you to be able to utilize the knowledge that you got from college maths, right? The knowledge surrounding indices, laws of indices, right? And then basically what we can do, we can square both sides of the equation, right, to eliminate this half here. I don't like it. So then if we say square, square, then can I just erase this? Then we'll get what? T square is equal, if you square this is 2 to the 1. So then if you square that, that will be now what? 2 to the 1 multiplied by 2, which will be 2 to the 2. The same thing for the pi. So then that will be pi square. This will be 2 square. And then L will be L to the half. A half times 2 is equal to 1. So then now we get L over G. Now, it simply means that we don't need to now find the square root of any L right here. So we can just go ahead and plot L with T square, but we don't have any T square in this. So then we're just going to take these values, the values in this row here for T, and square it. So then we have T square and the unit must also square. Right? So then if you now plot a graph of L with T square, L with T square, let us map this equation here to the what straight line equation. So then if we say, okay, T square is equal to Y, and the next variable is L, L is equal to X. Then my big question to you, what is M? Okay, we say that M is a constant. Is 2 a constant? Yes, it is. 2 squared a constant? Yes, it is. It is 4. Is pi square a constant? Yes, you cannot change pi square. Is G a constant in your location? Yes, it is a constant. So then, if we should just wrap up all these constants here and call it M, all of this would be our gradient. Then my question to you, what would be C? Nothing, right? We don't have anything for it right here, so then plus 0. So then ideally when you plot your graph, the intercept should flow right through the origin. Right? So this is just one example of how we can link the knowledge we get from knowing how to plot the straight line graph and analyze the straight line graph and link it to an equation in physics, right? So then listen up, we must be able to plot and analyze the straight line graph effectively. Right, now let us continue. But the aim of the game is to find G, right? So we say that M is equal to 4 pi squared over G. 4 pi squared over G. And we are, when we get the graph, when we plot the graph, we must be able to get M, right? Because M is equal to the gradient of the graph. So then the gradient that you find now, you're going to equate it to 4 pi squared over G. So then the only unknown in your equation would be what? G, because you know the gradient, you work it out. So then that value is equal to 4 pi squared over G. We're just going to do what now? Transpose. Remember, transpose, which would be the first unit on the website. Transpose. Right? You must be able to transpose. So let us transpose now and make G the subject of the formula. Right? I want G to be the subject. Simple meaning I need G alone to be on the left side of the equal sign. So I need to get rid of this G from over this side here. So then all I need to do is multiply by G. And if I multiply by G on my right side of the equal sign, I must do the same over here. So now I get Gm is equal to 4 pi squared. We have an m over here. I need to get rid of this m here, which would be the gradient that you find. So then to get rid of this, I must divide by m. And whatever I do on the left, I must also do it on the right. So then that cancels that. So then G is equal to 4 pi squared over m. And from that, you would get a value for G in your location. All right, folks. So then that's it, right? When you watch this video, you can watch it several times, right? And you know my office, right? You can always check with me pertaining to any issue you may come up with, right? Okay.